the shortest path that you could find. So that would be an algorithm that will decide how to give you directions from origin to destination for a Google map, for example. Right. So it should be quite, come to the top of your head, once you look at something like this one on slide 7, to tell what it is doing. So there are questions in like interviews or anywhere, like you're given a stack and you have to find out what this is doing, because usually there is no well-written document behind it, so you have to kind of reverse engineer. So in this slide, if can someone tell me what this algorithm is doing?
Looking for the largest number?
Right, it finds the largest, so it's an array that's given to it, and it essentially looks for the largest number, right? So it just walks through the array and finds the largest element of it and returns it, right? And then this is called a find function, and the question is find a time efficient algorithm. So to find the largest number, we have to go through all the elements in the array and check if that number is the biggest among all those elements, right? So we essentially have to walk through all and every single element in an array. There is no other way to do that, right? So if you think about it, how much time does it take to basically go through this algorithm? So if checking every element takes 1 second, let's say, I'm just exaggerating here, and then let's say my array has 10 elements in it, then how much time does this algorithm take?
Like 10 seconds or?
10 seconds, right?
Yeah.
Because you have to go through every single element, check it, and we assume that every element checking takes 1 second. So we have 10 elements, you have to go from element index 0 to element index 9 and check every single one at a time to make sure that your element that you found is the biggest. And then for memory, so there are time considerations and there is memory consideration. So in any algorithm, there are two considerations. There is a time consideration and there is a space consideration, right? So in terms of memory, how much space do we need to put this algorithm in place in computer memory, let's say? So we assume that the array is coming to it, right? So we disregard that because the array is coming to it. Then we have to see how many automatic variables or values are created inside for this find function. So this find function is going to be created in the computer stack in the RAM, right? So if we look at it, we only have one variable there, and that variable m is the variable that is being created. So it's just in terms of space, it's just one variable that's one temporary variable that's being created. This find function. How about a sorted array? So if you have a sorted array, what happens then? Do you think that this find function is efficient for a sorted array? So instead of having a random array coming into this function, we assume that array A there, I'm on slide number 10, array A there is sorted, let's say in ascending order. So
yeah, it will be very quick because it's sorted already. So you don't even need to go into the logical condition to get the largest number.
Oh, sorry, who's talking? Oh, okay. Yeah, that's right. So this algorithm is not then efficient for that, right? Because what this algorithm is doing is it's still walking. So you look at that for loop, right? So it's a for loop there, right? That is starting from index 1, it gives it to I. It goes to the last index in the array, which is n minus 1. And what it does the comparison. If AI is bigger than M, do the replacement, right? And keep doing that. So if your array is sorted, why do we need to do that? We just need to just return the last index. If let's say this array is already sorted in an ascending order, then there is no need to do such an algorithm. So what I'm trying to imply here is it is important to see what's your inputs, and what you're trying to do, and if you can fit the purpose. So not every algorithm is fit for every input, and not every input is fit for every algorithm. So we have to always understand our constraints and set up properties that we are trying to solve for, and go about it. Right, so this is another example. Think about computing the nth Fibonacci number. So the way that the Fibonacci number is being solved, it takes the two previous consecutive numbers, it adds it together, and that becomes the number that's coming next, right? So if you add 0 plus 1, next number is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, and so on. So what we have here, I just found that I can use the pen here. Hold on. Switch. Right. So what we are doing here, we are basically pen adding. I did this pen. Yeah, there we go. 3, and then 2 plus 3 is 5. 5 plus 3 is 8. 5 plus 8 is 13, and that's what the Fibonacci number is, right? So that's the algorithm for it, right? So if it is negative, or 0 or negative, so you enter the number of the number of Fibonacci's you want to have, and if the number is 0 or less than 1 or less than 1, you just return it. That number is the Fibonacci itself, right? If it's bigger than that, then you are trying to do some recursive call, right? So that's a recursive call there, because we are calling the function itself, and the function is fib. So this is our function. We're calling the function itself, but this time we're putting n minus 1 and n minus 2, and we're just adding them together. Okay, so this is the algorithm for Fibonacci number. That's a Java implementation of it. And let's look at a different algorithm. So we're gonna do the same, but this time with iteration. So this approach here is iterative, right? Iterative approach, and we have a for loop there that you're walking through it, and we're gonna do the same calculation of fi minus 1 plus fi minus 2, putting that into fi. So you see the implementation of it. I think that's a Java implementation as well. So now the catch is we have two different ways. One way is recursive. Okay, so you recursively call the fib function over and over again. The other way is iterative. And now the question is, which one is better, in terms of time complexity or time efficiency. Okay, so that's what the question is essentially.
Are you writing something to the screen? Because
yeah, do you guys see that?
No, I don't see anything.
It kind of froze or freeze. I don't know.
What?
Yeah, we don't see anything on the slide.
Ooh, what's going on here? Do you guys see it?
Okay, now we see it. Yeah.
Okay. So let me go back. Right. So you guys saw these right? You guys saw these, right? That's what I was trying to say. So that's a recursive call. We were trying to call the Fibonacci recursively. And then for part two, what I'm saying is we have the iterative approach. We just have a for loop in there, right? So this is the for loop we have, and we do the same thing. So instead of calling the function itself, we are using the for loop to calculate us the same thing. So there are two different approaches. One is recursive, the other is iterative, right? And now the question is whether we want to see which one is the faster one. Okay. And so I used to do this like a long time ago. And then in terms of running time, if you do recursive, it takes 5 seconds. And it appears that if you do the same with iterative approach, it takes only 7 microseconds, okay, on some arbitrary machine that you have, right? So so that's another reason for. And then there's a bonus question: How can we make the recursive approach run in almost the same time? So does anyone have any answers to that? Like, how can we make the recursive call to be fast, closer to iterative approach? So if you go back, this was the recursive call. Right? So we have this function. So if you guys look at this function, it is calling itself, right? So the key answer is for these two calls. So instead of having these to call themselves, how about if we save the answers as we walk through somewhere? So if we cache them, we essentially can have a quick access to those numbers, and then we can do that calculation pretty fast rather than having the function calling itself, right? So the answer to these bonus questions, it's not a bonus. I'm not going to give marks for this, but the answer would be that you basically use some caching method or some lookup table to look at the numbers for those recursive calls. All right. Right. So Fibonacci is a basic example of why we care about algorithm efficiency. A well-thought algorithm can run faster. There can be big variation in efficiency. Okay. This is just to show the significance of different methods of implementation of a code of a algorithm. Yeah.
Mehdi, can I ask?
Yeah. Go ahead.
What did you mean by a caching table? What is that?
Right. So if I go to this one, the Fibonacci, right? So let's say let's say I have a table. You guys see my writing, right?
Yeah.
All right. And then F2 and F3 and F4. If I already know the results, I have it saved somewhere, right? So this is my N. This is the N value. And then this is like, I know F1 is 1 and F2 is 2. F3 is 3, F4 is 5. I already know the answer. I already have saved it somewhere, right? So if I have saved this, I just go and look it up rather than going calculating it. That's one of the ways that we can get rid of the recursive call over there, right?
So are you actually saving this, or do you mean?
Yeah, I'm making the assumption that we save it somewhere. We already have it saved, like we have a lookup table that
I see.
We're just trying to see how we can improve the Fibonacci using recursive call to be same as the for loop, the iterative. That's what we're trying to do. It's just like a teaser question.
Okay, all clear.
All right, so when it comes to efficiency, we have different options. We can do it experimentally, so we can, run a bunch of experiments and see, okay, which one is faster. We come up with some solutions. We just want to do some blueprinting or some testing to see which approach is faster. The problem is that experiments are time-consuming, expensive. You have to buy tools and perhaps servers or hire people to do that for you. And at the end of the day, they are not accurate. So there are different ways they go about it. So there's like methods like a stochastic simulation. So they say we are thinking of a normal distribution of a population of, I don't know, a number of inputs, and then we give it to our algorithm and see how the results will look like. There is another method that is called discrete event simulator, and for that there are books written. There's like a Q theory written for it. I'm not going to go through all of these, but just want to let you know that there are ways to basically come about how we can gauge our algorithm efficiency, and then there are methods to mitigate the fact that our results are not biased, and how we can generalize our results essentially there. How about if we want to estimate the efficiency before writing code? So I think the rest of this class will spend time into showing you how we can do some really quick way of calculating the efficiency, mainly in time efficiency, or the much of a time that it takes the algorithm to run. And you guys can quickly calculate that by just looking at the code. So the purpose of this class is to show you how we can do that. So there are different elements that we have to consider to determine efficiency. The running time of an algorithm depends on the input size. So we usually refer to the input size as n, and the function that to be solved has a dependence to the input size. So the function is fn. So the fn means the algorithm essentially. And the efficiency for any algorithm depends on the number of instructions executed. So we have to see how many instructions are going to be executed, and that will also determine the time that it takes the algorithm to run. Okay, so we are looking for nested for loops versus single operations. Those are the essential things that we have to look for. So if you look at this algorithm, this algorithm is 6 lines. You see the lines in here, right? Lines 1 to 6, right? You see my handwriting here. And let's say my input is, my n is 3, right? If n is 3, that means that we have 3 elements in my array: index 0, 1, and 2. Okay. And if you look at a statement 1, it's not going to be it's just going to be called from some other function. So line 1, how many times is it going to be executed? None. Line 2, how many times is it going to be executed? 1 time. Okay. You go to the function and you put the first index into m, and m is essentially a automatic variable. So you have something like I don't know, int m equal a 0. Okay, so that line should be executed 1 time. Then line number 3, we have a for loop there. Okay, the catch is to see how many times this for loop is going to be executed. So for I equal to 1 to n minus 1, so n was 3 to 2, do the following. So that line 3 is going to be executed 2 times, and whatever comes into the for loop is also going to be executed 2 times. Okay, so line 3, 4, and 5 are going to be executed 2 times, and then at the end of the day, we have to return whatever we have as a result of this algorithm. So we're going to return m, and that line number 6 is going to be executed 1 time as well. Okay. So if we sum all of these up, we're gonna end up with 1 plus 3 times 3 minus 1, where 3 was number of inputs, so that's 6 plus 1 plus 1. So for F3 we have 8. The execution time is 8. So let's say each line takes 1 second. This is going to take 8 seconds to finish this, to finish execution here. Right. So if we increase it from 3 to 8 now, we see a pattern. Okay, and the pattern is that line number 1 is never executed, 2 is executed once, no matter what, and the last line 6, line number 6 is also executed once. The rest are executed based on the number of inputs, and that is the formula we have there for running time of this algorithm, right? How about 100 times? So we see that line number 3, 4, and 5 are going to be executed 99 times, right? So what I'm trying to say here is that we want to define a new term that is called basic operation, okay? And we define it as the statement that gets executed most frequently. So that if n is going to infinity, what's essential for us are lines 3, 4, and 5 here, right? Because that's what it really matters for the essence of this algorithm, okay? Right, so that's what the definition of basic operation is, and I think we're gonna go through some of the examples here to review basic operation. Right, so count the number of basic operation executed for an input of size n, right? That's what essentially we have to do. And that will determine how long it takes for our algorithm to run, okay? Right. Right, so in this example, right, I said 1 plus 3 times n minus 1 plus 1. What is important here? What's the dependency here?
Is it the loops?
Right. The dependency here is the number of inputs, n, right? So it's a function that the rest of, you see values there, but there is only n, one variable there, and that variable is n, and n is the number of inputs, right? So this function here has only one dependency, and that dependency is n, which is the number of inputs. So what I'm trying to say is, as n goes to infinity, what really matters in this function is this part, n minus 1, because the rest are just a constant number, right? So is infinity much bigger, or 1 much bigger, or 1 bigger? I mean, infinity is humongous compared to anything else, any constant, right? So what really boils down is this function is dependent to n minus 1 there. You know, that's all it's dependent to. And I think here that's what slide number 21 is trying to imply, right? So for find function, what's really important, the execution time is n minus 1. Okay. Okay, right. This is another example. So the first question is, the function is called mystery. Slide number 22, we assume that n is bigger than 0. We are having a for loop in there, and we are returning a local variable s, but we are doing some operation in the for loop for that s. So first of all, can someone tell me what this is? This algorithm is doing? Just taking the I, multiplying it, adding it to the previous sum. So what is that? What is that formula? So S is 0 at the beginning, right? So you have the first time you have 0 plus 1 times 1. That becomes 1. Next time you have 1 plus 2 times 2. That becomes 5. Then you have 5 plus 3 times 3. That's 14. And so on. So can someone tell me what the pattern is here?
The sum of the first, well, the sum of a bunch of perfect squares. I don't know if you're, what are you looking for?
Right. So so this is essentially calculates that. You see that, right? So
Yeah.
that's 1 squared plus 2 squared plus 3 squared plus n squared. Okay. And for basic operation, so basic operation is essentially what it takes most of the time, or most of the number of counts. Okay. So what is the basic operation here? Based on the definition I already have.
The S plus I times I.
Right. Right. So we either have to claim line number 3 to be a basic operation or line number 4. So we have to choose, because both of those two lines are the lines that takes most of the time of this algorithm. Okay. And so if you assume that n is going to infinity, then essentially line 3 and 4 are going to infinity with that, right? So let's say, and so the convention we made in the previous slide for basic operation is we don't think of for loop statement to be part of the basic operation. So we say whatever is in that for loop is the basic operation. So line number 4 is essentially the basic operation here. Okay. So let me go back. Right. So the multiplication on line number 4 or the addition, doesn't matter. That's what the basic operation is claimed to be here. Right. So now the question is, how many times this basic operation is going to be executed for input size n? That's the next question. So to do that, I already talked about the sums. You know, we had some discrete math coverage in the last class. So to do that, what we're going to do is we're going to utilize that. So for every basic operation, we have a constant 1 in there. And for the for loop, we determine the lower bound and the upper bound, right? So we are essentially have a sum of I equal to 1 to n for every basic operation. And every basic operation is a value of 1 in that sum, okay? Now, this is going to be, I think I covered this, n minus 1 plus 1 times 1. You guys see my handwriting? Okay, and that's going to be n. Okay. So it takes, for this algorithm, it takes n times, whatever the unit of the time is, to solve this algorithm. Okay. Now we take this one step further. Okay, do you guys have any questions so far? What I'm trying to teach you is, by just looking at the algorithm, you guys should be able to say and do some calculation with sum. So you have to utilize the sum notation. That's one thing. And for every for loop or for every basic operation, we have 1 in here. That's how the correlation is. And then after that, you say, okay, it takes n times. Now, I want to show you more complex examples in the next slides, but I just want to see if you guys at least somehow intuitively get the idea.
Is the sum showing the correct one? Shouldn't it be n squared instead of 1?
The n squared is for what it does. It's not for the time efficiency. So
I
this
think-
is showing the time that it takes for this algorithm to run. It takes time n for the algorithm.
Oh,
to
I
run.
see. My bad.
It will be n squared if there's like another for loop inside of that.
Exactly. That's the next. So let's move on to the next. Next example there, because I think you just answered it. So now we have 2 for loops in here. Always any function, any algorithm given to you, the first question is, okay, what does this algorithm do, right? So you just want to get a sense of what's going on. So can someone tell me what this algorithm is doing? So what's the input of this algorithm? What does it look like?
A 2D array.
Right. So it's a matrix. We have a n by n matrix in here as an input. Now, what does it do? What does mystery 2 is doing?
Sum of all the elements in matrix.
Exactly. And so it's because it's a 2D array, it needs 2 for loops, right? One for the column to walk through the columns, and one to walk through the rows. And it is doing the sum as it walks through every single element in a 2D matrix. So we have we have something like a 2D matrix. N by n, and there are elements here, right, in columns and rows, and it's going through every single of them in here and adding them, right? So it's adding all the elements together. Okay. What's the basic operation? Basic operation is the statement that is executed most in an algorithm. That's the basic operation. So what's the basic operation in this algorithm?
Is it line 5?
Line number 5, exactly. I mean, we could tell that line number 3 and 4. Well, actually, line number 4, along with line number 5, are the basic operation. But the convention is not to take the for loops in the basic operation. So we claim that line number 5 is the basic operation because this line is the line that is having most of the operations, the most executable operations in this algorithm, right? So this line is the basic operation. Okay?
So what if there is another line in between those 2 for loops? There's 2 lines of basic operation then?
No, still it would be not line number 5, because if you check line number 5 is following orders from 2 for loops. But if you had a statement between line number 3 and 4, so if you had something here, I don't know, n or m equal, n plus n, something stupid here. So if you had something in between, it doesn't matter, because that thing would have run only n times, right? Because that's outside of the inner loop. Okay. Who was asking the question?
So like if it's like being executed less time, then that will be the basic operations.
Right. The statement that's executed most time is the basic operation there.
Oh, sorry, most time or
most
time?
Yeah. So what you're concerned with the basic operation is to see how much it takes for an algorithm to run. Okay. And for that reason, we are looking for the basic operation of it. All right. So that's question number 2. Now we identified that line number 5 is the basic operation. The last question is, okay, once we have identified it, how many times is the basic operation executed for input size n? Okay, so we have to resort to sigma notation for this. We have to resort to sigma notation. So I said for every basic operation, we use constant value 1. So we have a basic operation line number 5. I use pen here. So I say this is one basic operation, one basic operation. And we use that, and we use the sigma notation. So every for loop is 1 sigma. Okay, we have 2 for loops here. We're gonna have 2 sigmas. So I'm using line number 4 and 5 to construct my first sigma. So it's gonna be j equal to 0 going to n minus 1 of 1, right? So let's call this x. Then I'm gonna do line number 3. So I'm gonna do another sigma for I equal to 0 going to n minus 1 of x. So essentially I'm gonna end up with 2 sigmas of 1 j equal to 0 to n minus 1 I equal to 0 to n minus 1. So that's the resulting execution time for this algorithm. We call this Cn. Okay. So if you guys look into page 45 of your textbook, so this is going to be page 45 of your textbook. It basically explains the same matters that I'm explaining here. I don't know if you guys had a chance to obtain textbook. Okay, are there any questions? So what is the answer now? So we already did this in class last time. So that we solved from inside out. So for this one, this is what is it? N minus 1 plus 1 times 1. So it's going to be n minus 1 okay. So the execution time for this algorithm based on the input is n squared. In other words, this algorithm takes quadratic execution time to operate. And if you guys look at the previous one, so this algorithm, which had 1 for loop, it was a linear approach. As you grow the number of inputs, there's a linear correspondence with the execution time. For this algorithm, it's a quadratic approach. As you increase the number of inputs, the execution time goes to square of 2 based on the number of inputs. Okay, and that's the final result. All right, so I expect that there's no question. If there's any question, you can raise your hand or wave there. We can have a discussion. I think I have more examples. Example 4. Okay, things are getting more and more complex now. How about this one? What does this algorithm do? So this algorithm is called loops, and the input is an array. So this is an input. We have an array. Okay. There is a for loop there, and that for loop there is a while. Why don't you guys take a minute to tell me what does this algorithm do? The follow-up question would be what's the basic operation there? What's the algorithm doing? Anyone wants to discuss it? So can someone tell me what's happening in that for loop?
It's sorting the array by ascending order.
Right. Who said that?
Me.
Youngju? Okay, good. Right, so what's happening here is, as an example, we have an array 5, 2, 4, 6, 1, 3. If you look at it, it's basically sorting the array as it walks through it. And at the end of the day, you have a sorted array in ascending order. Okay, so this is what the for loop is doing, and in that for loop, there is a while loop. Okay, so essentially, AI on line number 3. So AI number 3 is going to a local variable. We call it V, right? So what is AI starting from 1? So that's the for loop here. So we have the for loop here, right? So I starts from 1. So A1 is 2, right? So we give 2 to V, and then we index J to be I minus 1. So J starts from here. So that's J. Okay. So I have, this is J index. So this is the index J, right? Starts from 0, right? 0. Now I walk into the line number 5. So why J is bigger or equal than 0, which is J is 0, and AJ. So what is the value of AJ at the beginning? The value of AJ is A0, which is 5, right? So I have an input at the beginning like that. 5, 2, 4, 6, 1, 3. It's an array. 5, 2, 4, 6, 1, 3. So A0 is 5. So while 5 is bigger than V was 2. So 5 is bigger than that. do the following. Replace AJ, so A0 with AJ plus 1. What is J plus 1? It's A1. So it's going to replace 2 and 5 essentially in the next run. That's what it has been done, right? Okay. And you're going to say give J minus 1 to J, right? So J was 0. So J was 0. Now J is going to be minus 1. So the new value of J is minus 1, right? And in the next time that we come back to here, because J is negative, we're going to come out of the while loop, right? And then we're going to reevaluate V, right? And V was 2. I believe that V was 2. And we're going to give that to AJ plus 1. So what is AJ plus 1? Zero. So we're going to give 2 to A0. That's what line number 8 is doing. Then we're going to come back to the for loop in here. We're going to increment I by 1. So I becomes 2. And then we're going to do the same thing again. So A2. So I'm going to go and do. I hope you guys are writing this down because I'm kind of erasing and rewriting again. So we put A2 to V. So A2. I'm on the second iteration in that for loop. So A2 goes to V, right? So what is A2? A2 is 4. So V gets the value of 4, right? And then J gets a new value. What is I? I is 2 on the second iteration. 2 minus 1 is 1. So J gets 1. So what I have here on the second iteration, J is here. J is here. The index, right? Its value is 1. And V is 4. So V is here, right, on the second iteration. And I'm going to continue that, right? So while J is bigger than 0, which is, and AJ, so A1 is 5, bigger than V, V is 4. So AJ is 5 on the second iteration. A1, so that's a J here, is 5, and V is 4. So 5 is bigger than 4. Yeah, that's true. So that means that go into the while loop and do the following. Put AJ into AJ plus 1. So what is AJ? AJ is 5. Put that into the following, to AJ plus 1. So A2, right, AJ becomes 5. Okay, so that's what's happening here. That's A2, right? That's what's happening here, and we are here. Okay, and then J minus 1, put that into J. So J becomes 0, right? And then while, again, we have to go through the while again, while J is bigger or equal to 0, which is, and AJ. So what is A0? A0 is 2, is bigger than V. What is V? V is 4. It is not, so it's going to come out and go to line number 8. You guys follow that? So what it is essentially doing at every iteration, it's going to that while loop and it's doing that comparison with the previous elements that it has already sorted. And if it's bigger, it's going to do the replacement. If it's not, it's going to keep it. Okay. And so that's how this array is going to be sorted. Okay. So this is basically sorting an array, right? So what's the basic operation here? I just don't want to go to the other slide because I think we need to have a discussion here. So the basic operation is the statement that has been executed most. Okay, the operation or the statement that has been executed most in an algorithm. So between line number 1 and 8 on slide number 28, can someone tell me that which one of these are good candidates for basic operations?
Line 6 and 7.
Right, line 6 and 7. Anyone wants to defeat that? Do you guys all agree that line 6 and 7 are basic operations? How about line number 5? Is there a possibility that line number 5 could be running, but it doesn't go to line number 6 and 7?
Yes, if it's like the array is already sorted.
Exactly. Or if it's a case that, you know, AJ is not bigger than V, so you already have covered this. You know, you already come up to this while loop, and you already do the checking here, but you don't go here because this will be validated to false, right? So in my opinion, this condition here, AJ bigger than V, is a basic operation because it has been executed most in this algorithm. Right? Right? So there is a real controversy going on in the community to basically decide what we should do in such cases. Okay? So we can make a convention in this course that anything outside of a for loop and a while loop should be a basic operation, right? Or we can make a convention that, hey, this is in fact the basic operation. So we have two choices here that we have to stick to, either line number 5, this is statement, or either line number 6. I mean, it can be line number 7 too, but I say line number 6 as well, right? All right. So in the exam, you guys could be basically, you know, let's just go crystal clear here that we assume that anything outside of the while and for loop to be the basic operation. So whoever answered line number 6, I agree with you. Who was it? Yutong? Was it Yutong? I don't know who raised up. Was it Alan Cho or somebody?
I think it was me that.
Oh, okay. Yeah. So line number 6 is the basic operation here. Okay. Right. So the same thing applies, right? You know, we use a sigma, and for every basic operation, we put one constant in here. So we have that. We put 1 in there, and we have the for loop in here, right? Going from 0 to I minus 1. And that should be I minus 1 plus 1 times 1 equals I. Oh, sorry, I missed the other one, the while loop there. So there must be there must be a while loop in here that I missed it, and that goes from what is it, from J. So I missed this factor in here too. So there are actually two sigmas, because we have, it's not just two for loops, we have a for loop and a while loop there, right? So a while is also a sigma there, because it's going, it's gonna be iterating through that. So let's go back, correct it. So we assume that this as a basic operation, so that's 1 in here, okay, and then we have the counters. While loop is a bit tricky in here because it doesn't have a counter in it. So what it has a J in that, and then the counter is here actually. So that's why J is starting from 0 and going to I minus 1. Because from line number 4, we have the upper bound, and then we know that the lower bound is from J equal to 0. So that's how much J can deflect between 0 to I minus 1. You have that line number 6 as the basic operation there. And we also have the outer for loop to be another sigma from 1 to n minus 1. So that's why it basically comes into two sigmas, because we have to take account for the while loop. The while loop is iterating. So once we have iteration, we have a sigma. And for loop is obvious. So that's another sigma, right? And then for the first one, which is a while loop, the trick is to decide what is the lower bound and what is the upper bound, okay? And so in this while loop, we see that J is operating on it, and J is starting from 0 and going to I minus 1. That's basically what's happening in this while loop in here. And the simplest part is, the outer sigma, which is going from 1, because I is going from 1 to n minus 1. So once we extract it to a sigma notation, it's really easy to do the rest, right? I mean, we have our own cheat sheets, but we can easily say that, okay, this is I minus 1 minus 0 plus, oh, sorry. Right, plus I minus 1 minus 1 plus 1 times 1, right? So this is going to be I, and then we have I equal to 1 to n minus 1. So you're going to have n minus 1 minus 1 plus 1 times I. So it's going to be n minus 1 times I. I hope I did not mistake. I think we have to go. Sorry, this is not correct. So what we have from the cheat sheet, I think in the last class I showed you that this equation is n times n minus 1 divided by 2. I think from the cheat sheet from last class, if you guys follow, that's the
n
equation.
times n plus 1.
Oh, is it n times n plus 1? Thank you. Okay. So let's see if I...
No, I mean, so it should be n minus 1 times
Yeah.
n in this case.
Yeah. I think it's because of the upper bound, which is n minus 1, it should be n minus 1. So anyways, you guys have to look at the cheat sheet over there and decide. And then the book has appendix A for it. So I have my book in here. I can basically quickly double check. Did anyone manage to get the book by any chance? Yes or no?
Yeah, I have the digital version.
Right. RNG equations. Right. So if you look at page number 476, I don't know if you guys can see that, but we have I, number 2. So we have number 2 that tells that it should be n times n plus 1 divided by 2 for the time that the lower bound is 1 and the upper bound is n, right? So now that we have the upper bound in here in slide number 33 to be n minus 1, so it should be from n times n minus 1 divided by 2. Okay, instead of plus 1, it should be n times n minus 1. All right. So are there any questions so far? The only trick that I see here is, or the challenge I see that is to just, make sure that you guys can convert the algorithm to the sigma. I think that's the only part that's the challenging part, right? And so in complex situations where, in here in line number 5, you have, a while loop, it's just a bit confusing to see what are the lower bound and upper bound in it. And I already said that we are, in this course, we are not taking into consideration the statements in a while or a for loop to be the basic operation. So anything that comes after it, we say it's a basic operation, and then we use the while or for loop as a sigma. And then for the lower bound and upper bound, we have to see how much the while loop or how many iterations that can the while loop go through. Okay, so for the while loop in here, we see that our j is a determining factor, right? And so that's why we have j here, and then we see that j is growing from 0 because of I minus 1. So when I is 1, j is going to be 0, and so that's why the lower bound, what the lower bound is, and the upper bound is I minus 1 because I can go to n minus 1 in here, right? So I think that's the only trick that you have to basically make sure you make it correct. And once you have your sigma, then you essentially have your formula there, and it's easy to basically do the operations. You can use the cheat sheet or appendix 1, whatever, page 476, to basically conclude what the results should be. So whatever this result is, this is determining the time, the counting time, or how much time it takes based on the factor n, which n is the input. So n is the input here, or number of inputs, number of inputs. And so your algorithm will take n squared minus n divided by 2 times to operate. That's how much the computation time of your algorithm for this particular algorithm in slide number 32 will be. So this is just to give you an idea of how things work. You can just quickly go through different algorithms and calculate the computation time. Okay, I want to pause here. I want to give maybe 10 minutes of a break, and we can come back to cover the rest of these slides. All right, I'll see you in a bit. All right, guys. So I think it's necessary to solve this example here. And let me see. Right. So why don't we spend some time, since we are starting fresh as a second session. So can someone just tell me, by just looking at this, it's example 5. Where is me? Just give me a second. Oh, there we go. So example 5, slide number 34. You guys are sharing my screen. Are you guys seeing my screen? I guess you guys are seeing my screen, right? So how much time does it take? So what's the counting time for this algorithm? That's what the question is. Right? So we want to see what's the basic operation here, right? So the basic operation is a statement that's being repeated most time, right? And in this algorithm, we're having 3 for loops. And what's the basic operation here?
Line 6.
Right. So the basic operation is the that multiplication of two two members, right? So that's the basic operation there, and we have to apply summation on that, right? So I said for every single for loop, we have 1 sigma. For the lower bound and upper bound, we just look at the for loop iterator and see what we have to apply there. So the first one, right. So the first one is this for loop. You guys see my handwriting? So we have sigma k equals 0 going to n minus 1. The second one is this one. You guys see my handwriting, right? Sigma j equal to 0 going up to n2 minus 1. And the last one, the outer one, is this one, sigma I equal to 0 going to n minus 1. Right? That's how the for loops are incrementing. And just we augment all those sigmas together, and that becomes our Cn function. Okay. Right. Can someone tell me what's the result of this?
Is it going to be n cubed?
Exactly. We can do a quick calculation. So let's do for the first one. So that's n minus 1 plus 1 times 1. So that's going to be n, right? So the result of the first sigma is n. So we have 2 sigmas now, n, 0 to n minus 1, 0 to n minus 1. So we have to look at our cheat sheet, and I think that's going to be, so that's the j incrementation, right? So that's going to be n minus 1 plus 1 times n. That's this part. So that's going to be n quad. And then we have another one. So we have the last one. So the last one is sigma 0 to n minus 1 and quad equal to n minus 1. So because this factor there is the incrementation factor there in the outer is I. So do you guys see my black page? Is I equal
Yes.
to 0 to n minus 1. I have it n squared, right? So this guy is not having any dependency with the iterator. So there is no dependency with the iterator. So that's why we don't even need to go and look at our cheat sheet, right? So n squared is like a constant to I, right? So what we have is n minus 1, which is the upper bound, minus the lower bound, minus 0 plus 1. This is from last week, times n squared. So these cancel out, and that's going to be n times n squared is equal to n cubed. So think of it as if you have 3 nested for loops, is n cubed. If you have 2 nested for loops, it's n squared. If you have 1 for loop, it's n. It's just how we can basically materialize or generalize our approach to solving algorithms. If you see an algorithm that is 1 for loop, the computation time of it is n, which n is the number of inputs. If you have an algorithm that has 2 nested for loops, the computation time is n squared. If it's 3, it's n cubed. All right, and so on. So I think we have some examples. So example number 6, input size measure, number n, right? So we have n inputs. Right, so we have a while loop in here, right? What's the basic operation? Either 4 or 5. So we pick to be addition, line number 4, right? And there's a catch, and the catch is the factor I is being divided by 2 in that while loop. I'm on slide number 35. So the while loop is not going to go up to n. Instead, it's going to be halved every time. So in the situations that you are cutting the problem by half, it's logarithmic. It's going to be logarithmic. So in this case, the counting time is log n base 2. This is base 2. This is base 2. All right. So I just want to give you a heads up that just don't just generalize as just see the for loops. You have to see how much I is going to be incremented or decremented. So look at the incrementation or the new assignments of I and the way that it's going to grow or decrease. That's going to determine how your algorithm is going to conclude based on time efficiency. All right. So I just wanted to show you different examples from different occasions so that you have seen different cases. All right. Now I'm going to flip pages. So we are going to generalize the approach. So we have best and worst cases. So the best case is the minimum time that it takes over the inputs of size n. The worst case time that it takes for an algorithm to run is called C-worst. Is the maximum over input of size n. So the maximum over input of size n, that it's the time that it takes for n inputs for that algorithm to run. That's the maximum time, and then we have the best case, which is the minimum time. We define it as such. Right. So we have an example here. So in this example here, we are searching for a key in a list of n items. Right. So we have our function called sequential search. There is an array coming, and there is a key coming with it. And we are essentially walking through all elements in a while loop. And we say while we are walking through it, if it is not the key, just keep walking, keep walking until you find that AI is equal to the key. Otherwise, you're going to return -1. So that's what's happening here. The input size, so you have n elements coming in because the array size is n. Basic operation. In this case, there is no, I mean, this and in here is kind of tricky because you could have had a if statement. So if I want to erase all these, if you look at it, this guy can be if AI is not equal to k, do I equal to I plus 1. So essentially in that while loop in here, this is essentially while, while I less than n, if AI is not equal to k I plus plus. Okay, so that's essentially what's happening in this while loop in here, right? And then, so that's why we're telling that the basic operation is that it is that if statement, right? So what's the base case and what's the worst case, right? So we have to see what's the best case. The best case is that we find the key to be the first index in that array. That's the best case. So the computation time is 1. We essentially go through this while loop once. The worst case is that you go through all the elements in that array until the end, and even you don't find that. So the worst case would be n, because the array size is n. So you're going to walk through every single one, right? Which one to use? We will focus on the worst case. So obviously, in any scenario, you want to see what the worst case is. The best case, we don't really care. And right. So unless otherwise we don't specify, you should always analyze the worst case. In some cases, the best case is worst case. I think I have an example coming after. Right. So consider the algorithm to find the largest element in an unordered array, right? The largest element in an unordered array, you never know what's the best case, and what's the best case, and what is the worst case, because the array is not ordered, right? So you don't know where your largest element is located, in what index it is located. So you have to still walk through all the elements. So you wouldn't know which one is the best case, which one is the worst case. I mean, the best case is essentially the worst case, right? You're just tossing a coin to see which index has the largest element in an unordered array, right? All right. So are there any questions here for the discussion of the best case and worst case scenarios in terms of computation time? I just want to make sure that you guys are understood. Okay. So we have the next slide, implement n factorial, right? So n factorial is n times n minus 1 times n minus 2 times and so on, right? Times 1. Okay, that's what the n factorial is. Using for loop and determine its basic operation and basic operation. Okay, so this is an exercise in class exercise. I want you guys to spend 10 minutes here to use iterative approach, use the for loop, not recursive, for n factorial, and determine what's the basic operation of it and what's the basic operation count. So that's what it means by that is the CN. Okay, so determine its basic operation and basic operation count of it. So time is 7:56. Maybe we have some discussion at 8:05 for this. Okay, so I think I can quickly. Is there a way to share your screen? So if someone wants to type in here, how can I do that? Do you guys have any idea? Pause, record. Okay, so if I want to give someone. Yeah, I can make one of you host if you want to show me your code. I don't know how you guys have written it. I mean, even if you've written it on a, I mean, if you've written it on a, you know, on a piece of paper, you can just show that. But if you've written it in some like editor, you can share your editor with me, and we can go through that. So essentially, you want to show me your n factorial algorithm. So the algorithm is iterative algorithm for calculating n factorial. It's just a function that runs a for loop. Is there anyone who is volunteering here? So you could possibly have implemented that in Java or maybe Python, and I can, if you raise your hand, I can give you access to share your screen. So you can show class how you've done it, and then you can discuss what's the basic operation, and then what's the CN, which is going to be a signal. Okay, so G.
Oh, that's me.
Raise your hand.
Yeah.
Okay. Let me see if I can give you access. Yeah, I'm trying to find you in my list in here. What's your? Oh, okay. I found you. Make host. Okay. Can you share your screen with us?
Sure. Give me a second. Okay. So
Oh,
here's
nice.
here's what I got for the equation. I'm not sure if I'm getting this right because I'm still digesting it.
Yeah, that's correct. Yeah.
So if you want to do it from n to 1, you can just start it from 1 n to n, and then you would just timing the number to itself. So the basic equation will be the p times I here, and then because you need to go for every element, so the c will be n.
Right. So if you put that in the sigma notation, it's going to be sigma I equal to I equal 1 to n, right?
Yeah, 1 to n.
And then we're going to have n minus 1 plus 1 times 1, and that's going to give us n.
Yeah, that will be n.
Okay.
Yeah.
Okay. I think this example was simple. It's just to get you guys started, get your hands dirty with it and get you guys started with the work. Okay, good. Good. All right, so let's go back to my discussion here. All right. Okay. The next topic is big O notation, and and the notation for that is obviously big O, and in that it should go some value which we're going to discuss here. So slide number 41. You guys have seen these, so that's the counting time, right? And now that the question is, we have seen n quad, we have seen log n, we have seen linear n. There are cases that in last class for, I believe for mutations, we saw, for mutations, there was an example of number of students who can sit in a class. We saw that it's n factorial. And then now the question, which one is a better algorithm? So what I'm trying to conclude here is that in some cases that you're writing algorithms, for the same problem, you might come up to different approaches. And once you do the counting of execution time, you can come up with different numbers or different equations. And then you have to be able to say which algorithm or which method that you've used is faster. Okay, and this is for that. The linear approach is as you're increasing n, the value of your function will increase linearly. That's a linear approach, right? That's just a straight line, one-on-one dependency. However, for quadratic n squared, you see that it's going to grow much faster to infinity when we are comparing it between the linear and quadratic, right? So in slide number 43, I'm giving you the entire spectrum. So log n is the best, the slowest in terms of growth. Linear is next, n log n is next, n squared, n cube, exponential, and I believe that n factorial sits somewhere here. So the algorithms that their counting execution time is n factorial are the worst. The algorithms that are having log n are the best. So this is the best. This is the worst. Okay. And that has to deal with the order of growth. And the order of growth means that as you increase the number of inputs on the x-axis, how much the value of your execution time function, Cn, will grow. Okay, so that's essentially the main topic of this class. That's what we've already discussed in this class. Just to give you an idea, for log n, if we change n from 10 to the 6, okay, so we are sweeping n from 10 inputs to 10 to the 6 inputs, and if we have different type of algorithms, you see that for n factorial, it can take 5 billion years to operate, just for when n is 100, let alone the rest of it. So it's just well enough to keep us busy for the next 100 billion years. Okay, so that's what I'm saying. It is really important that how you develop your algorithm and what type of a timing complexity it is gonna end up having. Right, so maybe you can add this part to your cheat sheet. So as I said, log n is the lowest and n factorial is the highest. And there is the idea notion of big O. And big O looks at a function such that you can always operate underneath it. So in other words, big O is the maximum or the worst case that you can get with your function as you deliver the job throughout your algorithm. So it says for n's that are bigger or equal to 0, right? So we assume that for n's that are bigger or equal to 0, so n's that are bigger or equal to, n naught, for those, my function will always be underneath a CGN function. Okay, and so this function would be what it goes inside your big O notation. So our job here is to find that GN function. Our job here would be to find that GN function. In other words, our job would be to find the worst case scenario in algorithms. So when you're writing your algorithms, you have to look for worst case, and for that you have to resort to finding the for loops, the while loops, the conditions, the basic operation, and do the sigmas. That's what you have to essentially do. Right. So on slide number 49, what I'm discussing here, there are cases that you have a number of for loops in different functions, and you have to add those together. Right. Now the question is, what is the big O now? Okay. So the big O will take the biggest one in terms of growth. And if you guys see up here, I have put that in your, as a cheat sheet. You guys can copy paste it, those values. So for the example number 1, N3 is the biggest in terms of growth. then is n, and 4 is obviously a constant. So in terms of growth, n quad is the biggest. So when you want to construct the big O, you always put the biggest one. So and then you get rid of the constants. So in here, for this particular algorithm that is being shown for number 1, n quad is the time complexity of this algorithm. So let's say we have an algorithm that's a combination of 20 times n quad plus 500 n plus 4. The notation, the big O notation, would be n quad there. Okay, that's how you have to go with it. Next one. So here again, you look at your cheat sheet up there in terms of the growth for this one. N squared, obviously this one is like less than constant. So 4 times n squared plus 10, this is the critical one. So that would be O(n) squared. The order of growth is O(n) squared. You know, same here, n squared. So that's n times 2n plus 1. So that's going to be 2n squared plus n. And n squared is growing much faster than n, right? So for that reason, the big O notation would be to pick the biggest one, which is n squared versus this one. All right. Three log n plus 1, it's log n, right? 3 log n plus n. So is log n growing faster or is n growing faster? Which one? So if you go back to slide number, so in this slide you can see that slide number 43, is log n growing faster as n goes to infinity, or is it that n growing faster as n goes to infinity?
It will be n.
Right. So in terms of time complexity, we always do the worst one, take the worst one, and here in this example it would be O(n), right? So O(n) would be the answer to this computation. How about this one? For constants, it doesn't matter. It's whenever you see a constant, just put O(1). You know, when you have a constant, just put O(1). How about this one? Again, same. It's a constant value. It's gonna give you a constant value, so it's gonna be O(1). Right. So what I'm trying to say here is that it doesn't matter if you have a linear factor. So if you have n or 2n or 3n or 4n, at the end of the day, n squared is growing much faster. So so if you have, I don't know, something like 2n plus 8n plus n squared, like if you have an algorithm that demonstrates that in terms of you know, computation time, if you want to show it with big O notation, you pick the biggest one, and the biggest one is the n squared one. Okay. Another example, if you do for n3, I think this is gonna be n3. So if you have some algorithm that says, you know, n cubed plus n squared plus, you know, log n. So in this kind of algorithm, as an example, you have to put the biggest one. So n cubed is growing much faster than n squared, right? In fact, you guys can draw it. Like if you go to MATLAB, you can draw this. You can draw linear, you can draw cube, you can draw square, You can draw a log, and once you draw that, you can compare the results with what I have in slide number 43. So if you go ahead and draw it, it will be same as slide number 43, right? Okay, so we have an example here. Again, here we are trying to find the maximum, right? So find the max element in this array. What's the basic operation here? Slide number 51. So we always look into the for loops. So if you have two nested for loops, we look to the inner one, right? So in this case, the comparison that is coming after the for loop is the basic operation, right? And then we have to do the sigma, and the sigma will take the I from 1, so I equal to 1 goes to n minus 1, and the basic operation is 1 there, right? So that's what we are going to conclude there, right? So it's going to be n minus 1 plus 1. Sorry, it's going to be n minus 1 minus 1 plus 1. So we're going to have n minus 1 minus 1 plus 1 times 1. So it's going to be n minus 1. Okay. We already have done it in different examples. So once we get here, the question is how we can show that in a big O notation. Okay. So in this example, there's just a one for loop. It's pretty simple. So what we have here is that we have a sigma that gave us n minus 1. So n minus 1 is our Cn, and we want to show that in O Gn, and G should be the upper bound, right? So we have to see if n is growing faster or 1 is growing faster. Obviously, n is growing faster. So in this example, with big O notation, the order of growth for the upper bound for this algorithm is On, right? It's a linear approach. Okay. How about this one? So this one has 3 for loops, right? I think we solved it with 3 sigmas, and we found that it's n cubed. So the order, the big O notation for it, the upper bound would be On cubed, right? We already solved this. Okay, good. How about this one? So we have 2 for loops here. I can say from the top of my my head that this is going to be n squared because we have 2 for loops, so 2 for loops there, and then we have to do calculations for that 2 for loops, right? So we have 2 for loops here. The first one is the inner one, so it's j equal to I plus 1 going up to n minus 1 basic operation one, and there is the outer one. So this is the inner, and this is the outer of I equal to 0 going to n minus 2. So if you guys keep solving for that, you will get this finding, and you have a quad and a linear. And then the worst case between these two, which one grows faster is the quad one, right? So it's O(n) squared. All right, so that should conclude our first slide sets for tonight. I just want to see if you guys have any questions for time efficiency. Basically, this is just to give you an idea of how we do, basic calculations for finding if how an algorithm is growing. And actually, this is going to be an interview question. So if you guys are applying to different companies, for sure in Amazon, big companies like Microsoft, Amazon, they're going to ask you such questions. So you're going to write an algorithm, and they're going to ask you, okay, what's the big O, or what's the time complexity of it? And you should be able to write sigmas and show the same way I'm showing it to you, to just argue that why you think that your algorithm is outperforming the way that the opponent is asking, for example. Okay, so you have to learn it essentially. So I have some try it for homework. I think I'm gonna put lab assignment 2. I know that the lab assignment 1, I made a mistake and put the deadline to be next week. That's fine. You guys have plenty of time for it to submit, but just make sure that you don't submit late. And then for lab assignment 2, I'm gonna put some questions about big O and basic operation, and how we just did things in class for calculating the execution time. So if you guys have any questions, you're more than welcome to ask it now. Otherwise, I want to take 15 minutes of a break time, and then we can come back and start at 8:45 for our second slide set.
So is deadline today or next week, or like March 18th then?
Well, and Nadi, first of all, I have to see your face before.
Oh, come on, man. All right, hold on a second.
I'm so interested to seeing you, man. I miss you so much. In addition to the fact that it's a rule of, I mean, we want to respect others too, right? I know that you're perhaps naked, sleeping in bed, but it's not a good time now. Maybe you can save that for any time other than the 4 hours that you're having, right?
Sure.
So I think the deadline is 18, and 18 is next Monday, right? So usually we have 1 week, but I don't know what happened in the calendar that was basically typing the deadline for it, that it concluded to be 18. So for assignment 1, it's 18, but usually we have 1 week only to submit our assignments.
Okay.
All right, guys, so let's come back at 8:45, okay? I see you in 15 minutes. Thank you.
처음으로 마스크 판매한다고 하면 이메일 뭐라고 써 있어요?
이메일 뭐라고 쓴다고?
이메일 제목을 뭐라고 써
마스크 판매. 어디다가 써요?
그래픽 석세시장 있어. 그게 단순이죠.
제목 때문에?
아, 내용은 뭐 실제 충분히 알겠는데 제목을 어떻게 해서 그래픽 석세스 오픈 날짜와 마스크 사용
마스크 판매에 관해서 많아요. 요즘 헬스에 누구 아는 사람 있어?
마스크 김민 스텔라 김인데 언니예요.
마스크 판매에 관해서 오늘 청년 마스크를 판매하는 한국으로부터 마스크를 들여와서 판매하는 청년 사업가입니다.
아니 뭐그 쓸만한 많지 청년사회고 또 이렇게 어려운 이민자들을 도와주는 사회에다가 조금 더 기능성 숨쉬기 편한 기능성 마스크를 조금 더 싸게 납품을 하고 싶은데 혹시 댓글을 써보시거나 이 이메일을 제가 보낼 수 있는 담당자가 있을까요? 대충 이런 식으로 이런 식으로 쓰려고 하고 어차피 미주한 본전이잖아.
요즘 와서 혹시 마스크를 팔 수 있는 마스크를 혹시 사주실 의향이 있으셨을지 아니면 뭐 공급할 때는 판매할 때를 연결해 줄 수 있는지 알고
서비스가
싶어요.
정확히 이민자를 도와주는
이미전 후세 같은데 그 기관에 연결된 기관이 또 되게 많거든요.
내 말이. 그리고 나도 어쨌든 이민자로서 사업을 하는 사람이니까 나도
그러니까 뭐 혹시 도와주실 수 있느냐 이 마스크 판매에 대해서 어디 다른 곳을 소개해 주거나 아니면 뭐 직접 사용할 수 있는 하여튼 도움을 주셨으면 합니다.
혹시 제가 도움을 받을 수 있는 방법이나 프로그램 같은 것들이 있나요?
알려주시면 감사하겠습니다.
그런 식으로 뜨고 물어주면은 넣으라고 그렇지 않는데 뭐라고 하나 알려주려고 그랬지. 자. 냄비 좀 풀게.
이게 뭐
이게 너무 있네.
All right, guys. So let's continue our discussion. Oh, okay. I'm gonna upload the next slide sets, and which is chapter 3 about brute force. So you should be able to find it under content. Okay, so under content, week 2, there is week 2b underscore brute force. It's a PowerPoint presentation, same slide as before. Just pick it up from there, open it. So the first 8 slides, I'm not going to cover those because those are what we've discussed, and you guys can go and read it. It's just about the big O notations and the execution time as what we've been discussing for the past 2 hours. Now, if you flip to slide number 9, that's where the essential, actually that's algorithm class where the starting point is. So what we've been discussing is just the intro to the algorithm class. And I just want to give you a heads up that we are in the following. So what we're going to do, okay, let me share with you my slides so we can walk through it all together. Right. Okay. Share. Okay. You should be able to see my screen now. Is that right? Okay. And brute force is covering chapter 3 of the textbook. It's just a class of problems that can be solved with brute force. And brute force is just a plain approach to solving problems. It's like a 5 cents approach for providing a solution. Like if you provide a solution using brute force in any kind of an interview, the next question would be how you can improve it. That's essentially how it works. So just to give you a heads up and the direction of where we are heading, we are. Oh, come on! I'm just trying to write pen, and then red, and then. Oh, how can I go to? Yeah. So you see my black screen here. Chapter 3 is covering brute force. Why is it not writing it here? Oh, okay. So chapter 3. Okay. Brute force. That's what we're covering now, right? Then we're gonna move on to chapter 4, we're gonna look at a different class of problems called decrease and conquer. Conquer. So it's just a different way of solving problems. The way that we solve problems, the first way is like brute force. A different way, another way which we're gonna cover next week is gonna called. It's called actually decrease and conquer. And then we're gonna continue that discussion, move on to the next chapter. We're gonna look at divide and conquer again. Divide and conquer. And then chapter 6, we're gonna look into transform, and conquer. So again, so this is a series of conquer classes of problems that we can solve. So we can decrease and we can solve problems by decreasing and conquering the question, the algorithm, or we can divide the problem and basically solve it, or we can transform it to a different world and solve that. Then if time allows, we're gonna look into chapter 8, which is dynamic programming. So that's the chapter 8, and in that we're gonna look into Floyd and Warshaw's algorithms. So this is essentially what I have planned for this class. We're gonna cover these 5 main topics, which is like around 80% of the coverage of any algorithm class. Obviously, if you guys go ahead and take an advanced class in algorithms, you're gonna look into learning methods. So there are learning methods that you're not covering in this class. Okay, so maybe I have to be showing it here. So we are not going to get into learning methods in this class. Not going to cover this. All right. So the first is brute force, and there's no real formal definition. It's just a class of problems or different approaches for problems that can be solved, and it's quite obvious and straightforward. And in this method, you're not trying to be efficient. It's just easy to implement, and the force is coming from using the computer. So let's say you've given all the power of the world, and you just go crazy with developing the way that you think it's right. You just do it. It's like a 5 cents approach to solving problems. So the opponent of brute force would be sophisticated solution. So let's say as a class discussion. So we want to find a name in a phone book, right? The brute force approach is you go to every single page or every single name in your phone book to look for the name. A more sophisticated way is you have a ranking in your phone book, and you go to that particular letterhead, and you just browse things based on the order, and you basically take it from there. Calculating a Fibonacci number. The brute force is that you can have a for loop again to just do the calculation there, or you can do a recursive call to do the calculation. A better approach is that you basically, as I said, you cache different numbers of Fibonacci somewhere, and just do a lookup table for a one-on-one quick access. So in this class, we're going to look into sorting problems, string matching, password crack, And last but not least, there's a knapsack problem. That's how just sets the ground for how problems are looking like. So for the first problem that you're solving, there are different sorting algorithms, and we're going to look at selection sort and bubble sort. Those classes of sorting will fall into brute force algorithms. And so for selection sort, the way it works is that you scan the array, a given array. It's just unordered list, and in that you find the minimum. Uh, Basically the minimum number, and you swap it with the first index, and you keep doing that. Next time you scan the next minimum, the next lowest number, and you keep doing that until you have your sorted array. All right, so I would like everyone to take your time, maybe 10 minutes. I think 10 minutes is sufficient for this. Write an algorithm that you're given a known array, and you can sort it based on selection sort. Just keep in mind that selection sort is a brute force algorithm type. Okay, so you guys can develop it in Java, C, C++, or any way you like, maybe Python. So at the end of 10 minutes, I want you to share your screen. So one of you just raise your hand and let me know if you're ready.
진짜는 됐어. 한국에서 샤넬백 가격 올린다고 해가지고 봤어요?
한국에 샤넬백 되게 가격이 낮아니까 올리면 올릴수록 잘 팔리냐.
올리니까 거의 800만 원.
올린다고 우리나라 줄 서서
우리 여자애들 샤넬을 5초만에 한 대씩 외우잖아. 근데 위험하다. 다음 주부터 다 열고 가지. 와, 또 떨어져. 와, 너 또 그래, 이 서울 근데 그거 아직 아무런
그러니까는 임상 실험을 제대로 안 한 상태인데 그냥 이렇게
의미하고 쓰겠다.
일단 임상병 공급병 근데 뭐 이래도 죽고 저래도 죽고 뭐 그런 거
그럴 바에는 쓰고 죽는 게 낫다.
왜 해보고 죽을 수밖에 없는데 근데 지금 11일이라 발표
그거야말로 전형주 말을 빌리면 프로틴 가루보다 더 믿기 못 되는 거야.
혹시 뭐 어떤 부작용이 있을지 모르지만 지금 주세가
죽는 것보다 나으니까 최악의 상황에 쓰겠지만
어쩔 수가 없는 상황.
미국이 그거일 거야.
근데 누구라도 뭐다 죽어갈 거면 쓰겠다 하지 않나? 그렇게 주장이야.
렌베르 뭐라고?
렌베르시드.
렌베르시드.
그게 원래 그 뭐지 에볼라 바이러스 개발된 작품인데.
So anyone want to share your screen? Yeah. So Zhejiang, excellent. Let me share my screen. Give you the make host. Okay, you have it all. You could share.
Okay, so here's what I got for selective sort. So you want to go down to, for every element, you want to check if it's the smallest, and then once it's the smallest, you assign it back to the S, or you assign it back to the index.
Right. So you are having a for loop there, and you are walking through the list, and every time, why are you having two for loops?
Oh, it's just pretty much making sure that this is the smallest number in the loop. Sorry, in the array or
Right.
the collection, and then once it's the smallest, and assign it back to the index, and then go to the next one.
Right. Yeah, I think that's a correct one. I think your algorithm is right. Has anyone done anything similar, or is there anyone who wants to share a different approach? So I think your algorithm is correct. Okay. Let's just look into sharing back the screen. Okay. So pseudocode for that, as Zichang told us, you guys are seeing my slide, slide number 15. Yes. Okay. So just let me know if you are not seeing my slide. So slide number 15, selection sort. We have a for loop that is going from I equal to 0 to n minus 2. And we put the index to that, right? And then we have a second for loop that is starting from j to be I plus 1 to n minus 1, and a min is a0 here. If it's less than ai, if it's less than aj, this guy here is j. Then we put j into the min. So this algorithm is basically playing with the indexes. Okay, it's just playing with the indexes, and if that's the case, it is going to swap the real numbers at the last line. So it's quite in line with what Zichang was showing, except that, you know, for the second for loop, I don't know if you did this, but I think here it's playing with the index there, right? So what is the complexity here?
It'll be n squared.
N squared, yeah. So I think for n squared, because we have 2 for loops, right? All right. Right. So let's move on. Next is bubble sort. So selection sort is one method that you see that in brute force, we are essentially just walking through all and every single element and checking them, okay? And that's what brute force means. It means that there is no secret sauce in here. There is no intellectual property, or I don't know, any blink or any special idea going on. It's just going through every single one, compare one on one. Next, we're gonna look at bubble sort, right? So selection sort is kind of a brute force algorithm. Bubble sort is also another algorithm in brute force category. The reason why it is, it's because it makes multiple passes through a list, and in each pass, when it's going through the list, it looks at the adjacent items and exchange them if they're out of order. And then in each pass, you're going to put the next largest value in the proper place. So basically, we are bubbling up as we walk through the list. So this is an example. So we have an array. It's not ordered. It's unordered. 3, 2, 6, 4, 1, 5, and we want to order it based on ascending order. So the first we look at the adjacent, index 0 and 1. We compare the two, and we realize that if we are trying to order in ascending order, we have to replace, swap the two. So we swap 2 and 3, okay? Next is 3 and 6. So we compare 3 and 6. They are okay, we move on, okay? Next is 6 and 4. 6 is bigger than 4, so 6 should be pushed to the back, right? So we keep doing that. Next is 6 and 1. So we compare 6 and 1. 1 is smaller, so 1 comes, 6 will be pushed to the right side. And last but not least is 6 and 5. We have to do the swapping again, and that will place 6 to the end of the array. So can someone tell me what's happening here? We are essentially pushing the big numbers to the right place, and we come back again from the beginning and do the same thing for the next big number. However, the way we do that here, we are doing with the adjacent cells, and that's why we call it bubble sort, right? So next time we come here from the previous slide 18, we go to slide number 19. So at the bottom of the slide 18, we have 2, 3, 4, 1, 5, 6. 2, 3, 4, 1, 5, 6 here. You start things again from index 0. So 2 and 3 will stay. 3 and 4 will stay. right? 4 and 1 has to be swapped. We push the biggest number to the back of the array, to the right side. We swap it. 4 and 5 will stay. Okay. Now we have 2 elements sorted. You see how slow this algorithm is? We have to do it again. From this is slide 2, 3, 1, 4, 5, 6. 2, 3, 1, 4, 5, 6. Again, we do it again. We go to the index 0. 2, 3, they will stay. Right? 3, 1, it has to be swapped. 3, 4, it will stay. Okay? Then we have 3 elements that are ordered in ascending. We have to do it again. So slide 2, 3, 1 at the bottom, 2, 3, 1, 4, 5, 6. 2, 3, 1, 4, 5, 6. We go to index 0 again. 2, 1, it has to be swapped. 1, 2, right? 2, 3 will stay. 3, 4 will stay. 4, 5 will stay. So if you guys look at it, at the end of the day, this array is sorted in a bubble sort format. So the challenge is that you have to run it through 2 for loops, which the inner loop will sweep it every time, and the outer loop will reset it to where it was from the beginning and go ahead again. And you see that it's a bit you know, a time-taking process, obviously. So can someone tell me that what's the order time complexity? The counting time. So obviously we have two for loops, and because of that we have 2 sigmas, right? Right. So that's how the time complexity is looking like. And then when you're looking at efficiency, whenever you have 2 sigmas, it's going to be n squared. Okay. It's going to be in big O notation. It's going to be O(n) squared. All right. So if you guys go to slide number 23, there is a link that I have shared with you. If you click on that link there, it just shows you different ways that bubble sort is helping to sort different types of arrays. There are unordered type of arrays, there are ordered type of arrays, there are arrays that have been ordered reversely, and it shows you how much time it takes to order them, you know, side-by-side comparison. So I advise you to please click on that link that I have shared with you, so you can get an idea about how a bubble sort is operating. Let me see if I can share that with you. Right, so this is the page. So let's say I have a random array, I have a nearly sorted array, I have a reversely sorted array, and I have an array that is sorted based on some unique pattern. So once you play that, nearly sorted did it first, the second one. Random did it next. Reversed and few unique did it equally well. Okay, so let's do it again. See, nearly did it first, nearly sorted. So random will do it next, the first one. Few unique do it third, and then reversed does it last. So reversed is actually the worst case, and the worst case in our case is n squared. Okay, so if you have 10 inputs, it takes 100, you know, whatever the units of time it takes. All right, this is just to give you an idea how things are operating in the best case and in the worst case. So the best case was nearly sorted. So if you have an array that is nearly sorted, obviously it takes the least amount of time. All right. Good. Next topic is string matching. So for string matching using the brute force, what we're trying to do, we are trying to, I mean, you guys are having a project in this course. You have to think about these algorithms, right? So one of the projects I was proposing is, look at some textual inputs like a Twitter account or Twitter feeds or Instagram or Facebook feeds and look for harsh language, right? So one method that you guys can implement it is just the way I'm telling you in slide number 25, right? So what we have here, are you guys seeing my screen? Slide number 25, yes? Okay, good. So the pattern is compressed and we're trying to find this pattern in a text, right? That's what the goal is, okay? So this is how we do it using brute force approach, okay? The pattern is a string of m characters to search for, and the text is a longer string of n characters. So obviously n is bigger than m here because n is our main text and m is the pattern that we're looking for. So the problem is to find a substring in the text that matches the pattern. All right. So let's say we have a pattern A, B, A, A, and we have a text A, B, C, A, B, A, some random arbitrary letters in an array. Okay. So what we do is we start from the beginning of the text and we see if we can compare the first element of the pattern with the first letter in the text. If it matches, we go to the second element in the pattern and see if we can compare it with the second element consecutive to the text. If it matches, we do it again and again. It doesn't match, what we're going to do as a brute force, we go to the next element, right? The next element is B. It's not matching. We move forward the pattern to the next element. It's not. We move forward. It is. The second one is. The third one is. The fourth one is. Bingo. Then we have found the pattern there, and we return the index at which we found the pattern in that text. Okay, so the brute force approach for string matching is to go to every single element in your text until you find it. What's the worst case?
That you can't find it?
Right. At which point, how much execution time you have consumed, or have you consumed?
Like, let's say there's n element, then you have to go through every one of them.
Right.
So it'd be n.
Right. So you should kind of go to n minus m there, right? So if this is, let me see if I can type in here. So this is m, and the text is n number. So if you have to sweep this guy over all the way, it gets up to here, right? So it's going to be, you have to sweep it from here going all the way to here, right? That's where you have to stop. So it's essentially n minus m plus 1. That's the time, the worst case that it can take, right? Okay. Are there any questions here? Okay.
What's the big O for this? Is that just like O of n?
I think it will be O(n minus m).
Okay.
O(n minus m). I think it's coming after. I have to double check this. So it's coming on the slide number 29, perhaps. Yeah, this one. So there is m that I have missed in there. So we have to see why it is times m, right? So let's go over the algorithm first, right? Before we can answer this. So the brute force algorithm says align pattern at the beginning of the text, right? Moving forward, moving from left to right, compare each character of pattern to corresponding character in text until all characters are found, right? So we keep doing that. I just showed you how to do that. Or if a mismatch is detected, while pattern is not found and the text is not yet exhausted, realign pattern one position to the right and repeat step 2. So what we've done here is essentially we have gone through, so we align it like that. We compare one by one. If we see a discrepancy, we move to the next one in the text until we see a match. Okay. So let's look at the algorithm of this. Maybe if we look at the algorithm, we can find why that m is multiplied to n minus m there. Okay. So there's a for loop in here that goes from 0 to n minus m. So the reason that we have n minus m because we want to get to the end of, this pattern here. I don't want to go beyond, like if my pattern is at the end. So I have 4, 1, 2, 3, and 4, right? So my pattern is at the end here. So basically I have to sweep and stop here at this point. And this point is n minus m. So this index here is 0, and this index here is n minus m. All right. So that's where the for loop comes. That's for this part. All right. You guys see my marker there, right? And I have to initialize j to be 0. I think that's for the part that I'm walking through the list. And I'm saying while j is less than m, okay, I think that j is used for matching. And pj, the element in the pattern matching, is equal to ti plus j. So I is starting from 0, and j is being incremented in that while loop, right? So it's 0 plus 1, 0 plus 3. However the length of your pattern is, right? So j would be the length of your pattern. Okay. So the catch is if you have gone to the end of your pattern and have this condition here, and you have this condition here that is matching and correct, that means that your letters one by one are correct in the text with the pattern, right? And you have gone and you have arrived at the end of your pattern, because this condition will not be met after you receive to the end of the pattern, then j will be equal to m, obviously, you get out of the while loop, j will be equal to m, and then you return I, at which point that I is the index of the location where you found the first matching sequence. All right. Now the question is now going ahead and finding, converting this to sigma, basic operation sigma, and basically extracting that. This is going to be 2 sigmas, and basically based on that we will extract the big O notation out of it. That's what the exercise is. So worst case. So yeah, so the example of worst case is that we walk through it until we get to the end. Nothing is found here. We're gonna have m comparisons. So every time, I think the reason that why we are having that m multiply is because we are having m comparisons every time. So every time we have to do, so this while loop in here is doing that m comparisons. So this guy is m iterations. I think that's what it's going to give us. So it should be, let me wipe this. So this is sigma 1 j equal to 0, and it goes to n. Do you guys agree with me on this? The maximum that the while loop can iterate is m, right? Because j should be less than m. So this will give me m. All right, and then I have the bigger for loop, the outer loop. So this guy will give me the second sigma for I equal to 0 to n minus m. Okay, so I already had this. This was m, right? So I'm gonna have n minus m minus 0 plus 1 times m, and that's what the resulting answer is going to be. Do you guys agree with me on that? So it's going to be n minus m plus 1 times m. I think that's going to be the big O. So here we have 2 variables, n and m as mother. Okay. So I believe that's what the result is. Yeah, we have 2 sigmas, 1, 0 to m, and then 0 to, that's j equal to, and that's I equal to 0 to n minus, sorry. N minus m. Okay. All right, so we learned about selection sort, how it works, and the bubble sort, that it takes this much of a time, maximum, worst case, and selection sort and the bubble sort, and then the string matching. So these are different techniques that I'm showing you here. It's just a very plain technique, which is using the brute force, right? So you're assuming that you have all the resources to operate the quadratic operations in terms of time complexity. The next thing I want to show you, which is getting worse, perhaps selection sort and bubble sort are handy. String matching was okay. Password crack is the worst one. So when you're doing password crack, you're talking about security, right? How people can break your password. And nowadays passwords can be letters, uppercase, lowercase, and then some specific character other than letters and numbers. And the reason for that is if a dumb hacker wants to crack your password using brute force. So let's say a hacker has all the computation power of the world and all the Amazon Web Services and Microsoft Azure and all that to basically go ahead and calculate and be able to reverse engineer your password, then he or she has to guess every single possibility to find your password and be able to crack your email account, for example, considering that he knows your username. So we want to see what's the complexity of it, right? So M here is the number of characters to choose, and we assume that we only have 26 lowercase alphabets. So in this case, we assume that our password can only be 26, can only be chosen from 26 lowercase letters, English letters. N is the character length, right? So with knowing these two numbers, can someone tell me what is the time complexity? Or in other words, how many different guesses the hacker has to put in place to be able to hack your password?
M to the power of n.
So n is the character length. So I think right. M. So M is the number of characters that you can choose from. So let's say you have some space to fill up your password. So this can be your password, right? And at every location, you can put one possibility of M characters, right? So at this place, I have M possibilities. At this place, I have M possibilities. At this place, I have M possibilities, and so on. So that's going to be M times M times M times M, and that's N times. So you're going to end up with M to the power of N. Okay. So if you have, if you can have 7 characters, 7 spaces to fill up your password, it's going to be, and with 26 alphabets only, it's going to be 26 times 26 times 26. You get the idea, right? That's 7 times. That's 7 times. So that's going to be 26 to the power of 7, right? So what is 26 to the power of 7? 8,031,810,176. So that's how much trials you have to make if you want to use the brute force approach. Just 26 characters, because nowadays that the passwords are, worse than that. I mean, passwords are more complex. Passwords you can do uppercase, lowercase. You have to do uppercase and lowercase to just make it more complex. So that's even more than 26 characters. It's like, I don't know, 100 different types of options you can have for every single space in your password. So you can see that the hacker would have next to none opportunity if he or she wants to use a brute force approach to crack your code, crack your account, for example. All right. So this is one example of showing that brute force can sometimes be a miserable approach for such class of problems. Okay. Last topic of the day is going to talk about optimization problems that will use brute force, and we're going to look into knapsack problem. So with knapsack problem, we want to generate a list of all potential solutions. List of all potential solutions will tell me something about mutations, right? Or subsets. Even subsets is better, right? I'm looking for all potential solution as subsets of a set in a systematic manner. And we have to evaluate potential solutions one by one, and that's where the problem is, because if it's a brute force, we have to look at it one by one and disqualifying the infeasible ones and keeping track of the best ones that we found. So we have a knapsack, right? And we have different weights that we can put into the knapsack. The maximum weight that the knapsack can tolerate is 15 kilos. We have bricks of 4 kilos, 1 kilos, different values. We have bricks of 2 kilos and 12 kilos. So our inputs are the weights of bricks that we want to put into knapsack, and each of them are having values in dollars. The goal is to find the most valuable subset of the items that fit into the knapsack. Okay, so we want to see what's the biggest weight that we can fit based on these items 1, 2, 3, 4 at different weights and different values. The maximum weight that we can load to the knapsack is 16 kilos. All right. So when it comes to these class of problems, we have different options, and then we can look for different subsets. Okay. So with 4 items, let's say my set is 1, 2, 3, 4. Then how many subsets can I have? I covered this in last class.
2 raised to the power 4.
Exactly. So either your item can be in your subset or it cannot. So there are 2 options only for every item to be in a subset. So that's 2, and then you have 4 of those. So that's 2 to the power of 4. That means we have 16 subsets. In other words, we have to construct 16 subsets and calculate the augmentative weight in there to be able to suggest if it's going to fit into the knapsack of maximum 16 kilos capacity or not. So generate all possible subsets, compute total weight for each, and identify the feasible subsets. In other words, remove the infeasible ones, the ones that are not feasible. So here is the catch. So we have calculated all the subsets, their total weight, and we are going to remove the ones that are not possible. So for example, this one is not feasible. That's 17. We have to be 16. This one is not feasible. This one is not. This one is not. The ones that are closest to 16 is this one or this one. So which one of the 2 would you pick? Would you pick this guy, number 1, or would you pick this guy, number 2?
Obviously, number one.
Why?
More value.
Right. So it depends on if you want to pay. I don't know which side of the which side the problem is. If you want to spend less or if you want to spend more, depending to that, we have to see in terms of dollars which one is more cost effective, right? So we need to generate all subsets in here. Okay. And then I already told you that that's 2 to the order of n. N is the number of inputs. So the complexity here is 2 to the n, O 2 to the n, right? Because in subset problems, you're looking at exponential growth. So 2 to the n is the exponential growth, which is a terrible approach. So that's going to be 2 to the n exponential. All right. Right. So brute force is more of an exhaustive search algorithm. It's pretty responsive in small, very small instances. In some cases, the exhaustive search is the only way to reach out to solving problems. Here, I just have a slide for highlighting the strengths and weaknesses. And I think I have a few problems to suggest that you guys can go ahead and take a look. I would try to put up the second assignment by the end of this week. That will cover the time efficiency, big O notation, and brute force algorithms for class. And then from the time that I have released the assignment, you have 1 week. Hopefully, I don't miss the correct deadline this time. So yeah, stay tuned. Check your D2L and check your Slack for updates. If you have any questions, I know that some of you are having a conversation with me for your projects in Slack, which is great. I'm loving the conversations, but I would be happy to stay. We still have like 15 minutes left for class to finish. So if you guys have anything that you want to share, I would be happy to answer your questions. Thank you.
I guess I'll ask something. Well, you have to see my face first. Okay. So I wanted to know that can we use data frames and stuff for the string manipulation for our project?
Can you explain data frame? What is that?
So it's basically in Python you could convert an Excel file into how do I explain it? Basically a glorified table used by data science. So
right.
It would relate directly to my own. So I was thinking I could work with that.
Right. So once you parse that, it's kind of a parser, if I'm not mistaken there.
Yeah, I'm gonna parse it, but again, like there's a lot of data cleaning. So you said if the data is not like, if it's like ugly data, let's say, then
right.
cleaning it would also be a part of
denoising it, right? Okay, so once you do that, what's the goal of the project? You're trying to do a string matching there?
Form of, yeah, something related to that.
Right, it would be a great, like one line of research that I see. I mean, my background is, obviously research, and one line of a research that I see, I see it in different talks, and actually it's very very hot nowadays. If you guys can, basically brag or show it off if you've done it or if you could do it, is to look for, and actually Google and Facebook, Instagram, and all those social media are doing it. They look for harsh language and they identify it and try to filter it. So if you could do such a thing, such a project that it just parses the Twitter feed let's say. I'm pretty sure there are open. So I mean, Facebook has open APIs, right? That you can parse your live feed, and then you can filter the feeds that are containing harsh language. So you can apply that to your kids, right?
So maybe if I'm understanding this correctly, so something like let's say there's a live video going on, and then you decided to take the live voice which is coming in, decipher what that audio is, convert it into text, and then like maybe you could use it as hashtags and stuff, like figure out what hashtags they're using. No?
That would be equally a very fantastic project. Yes.
Okay.
Yeah.
Something like that. Okay,
So,
that sounds cool.
if you get that to that point, I would suggest that you submit your code to GitHub. I think there are summer school. Google has summer schools. I can share you the links there. You can send your code there, and perhaps there is a possibility that you work from Palo Alto next year. We can come and give you a visit there.
Okay. I will try.
Yeah, so that's the first stage. I don't want you guys to go beyond, because going beyond is just to look into adversarial models, because there could be attackers that can populate harsh language or different type of, to just bias the environment so that your algorithm will fail. But we are not going to that level, because that's what the state of the art is. The state of the art is just to look for authenticating the correct the correct behavior of humans as the way they speak or the way they type in social media, and find those and be able to filter it. But there are botnets that have been devised to write harsh language to just populate and fool such algorithms. And so I know that Facebook and Google in particular are looking at such cases. Alan, it looks like I'm in sitting in North Pole when I'm looking at you. Is it really cold there, Alan W?
Oh no.
Just had it on. Do you feel cold?
No, I don't.
It's hot in here.
I have the fan on, so I'm good.
Right. All right, guys. I think if there is anything in particular that you want to talk to me, individually, you can ping me in Slack. We could perhaps continue our discussion there. Otherwise, that should be it for this week. So you guys stay safe and keep coding. Keep simmering code.
Thank you.
Yeah, have a good day.
Yeah, thank you.
Thank you very much. Good night.
Good night.
Thank you. You too.
Good night.